Hello everybody. Right now I want to take a few moments to discuss a design idea that I have. It has to do with refrigeration systems. And refrigeration systems are basically identical to air conditioning systems. For the most part, this is going to deal with air conditioning systems of buildings. However, it can also be adapted to be used for various refrigeration systems in large refrigerated spaces, such as meat lockers or anything that, say, for instance, a restaurant might want. Okay, so what my design idea is, the purpose of it is to increase efficiency, decrease the total amount of energy consumption required to refrigerate a space, either air conditioning or in a refrigerated space such as a refrigerator or a freezer. I have an idea that's possibly been thought of in the past. I'm honestly not sure. Haven't done the research to find that out. But I figured I'd go ahead and put this on YouTube, and anyone that's interested in it can perhaps do something with it. Maybe you're a real estate developer, you're an HVAC technician, refrigeration systems engineer, whatnot. Might be a design idea that you could potentially use. For everybody else, well, I'm going to explain it, and hopefully, it might be something of interest to you too. But in order to understand refrigeration systems, there are a few basic things that we need to understand about heat transfer. So first off, I'm going to talk about heat transfer. Then I'm going to talk about refrigeration systems, the basic refrigeration cycle, and then I'm going to move on and explain exactly what my specific idea is. So getting into it, right now we're going to take a look at this heat versus temperature. So heat is on the y-axis, that's the letter Q. Temperature is on the x-axis, that's the letter T. Okay, so in order to understand how refrigeration systems work, it's important to understand that the basic concept is to manipulate this temperature right here called the saturation temperature of the refrigerant. We're going to talk about how that happens. Okay, but if you have a solid, for instance, and you continue to add heat to it, it's going to increase the temperature. So you're adding heat to it, you're increasing the temperature up until the point where it reaches this temperature right here called the fusion temperature. If you continue to add heat to it at this point, you're not adding any temperature to it. However, what you're doing is you're converting it from a solid to a liquid. And that is called a latent heat transfer. Anytime you add heat or you subtract heat from something and it causes a phase change. Anytime you add you add heat to something and it causes an actual temperature change, that's called a sensible heat transfer. So if you have a solid and you continue to add heat to it, again, once it reaches its fusion temperature, if you continue to add heat to it, it's going to go through the process of liquefying. It's going to go from a solid into a liquid. Sensible heat to increase the temperature right here. Latent heat to cause the phase change. Once it reaches a liquid state, if you continue to add heat to it at that point, once again, your temperature scale is going to increase. So once you've completely liquefied, you continue to add heat, you're going to add temperature to it up until you reach this point right here, which is called the saturation temperature. The saturation temperature is that temperature in which a latent heat transfer will cause something to gasify if you increase heat to it, or if you have a gas that's at saturation temperature and you subtract heat away from that gas, it's going to cause it to liquefy. So when you're starting to talk about latent heats, you're basically going to see two different kinds. You're going to see latent heat of going from a solid to a liquid, or vice versa, or you're going to see another latent heat type when you go from a liquid to a gas, or vice versa. Now, latent heat of fusion is when you take a substance and basically you travel this way on the graph. So you're traveling upwards and you're transferring something from a solid into a liquid. Vice versa, if you're going through latent heat of solidification. It's the same amount of heat transfer required to either liquefy, or the same amount of heat transfer that you have to subtract away from the system to cause it to go from a liquid to a solid. So this latent heat transfer is the same quantity of heat regardless of whether it's fusion or solidification. Same thing with vaporization and condensation. Okay, so if you're traveling this way, so you have what's called a saturated liquid. Once it reaches its saturation temperature, continuing to add heat to it is going to cause it to gasify. And when it travels upwards on this heat versus temperature, that's called a latent heat of vaporization. Or if you have a saturated gas right here and you subtract heat away from it, Well, that's then going to go through the latent heat of condensation. So the actual quantity of latent heat of vaporization or latent heat of condensation for any given substance is the same. Again, that just simply describes which way you're traveling on the graph. After a gas reaches its saturation temperature, to continue to add heat to it at that point, you are superheating the gas, and you're continuing to add temperature to it, and that's going to just basically continue on indefinitely. Okay, a few different notes that I'm going to discuss on here. Okay, in any given thermodynamic system, the total heat transfer is equal to the sum of the latent heat transfer as well as the sum of the sensible heat transfer. So right here, this is the total heat transfer. It's equal to the sum, the latent heat transfers, as well as the sum of the sensible heat transfer. In any given system, you might have more than one of those. You can have a total of 2 different latent heat transfers. You can have a total of 3 different sensible heat transfers. Now, something that's kind of important to note about fusion temperature and saturation temperature is that it's affected by pressure. So let's say, for instance, you're cooking something on your stove and you're using a pressure cooker. You seal the lid on it, you put it on the, put water in it, you seal it, put it on the stove, and as you heat it up, because it's a compressed space, it doesn't allow the molecules to expand. Consequently, the liquid water in there can't transform into a gas. Because of that, you can actually have water that is higher than 100 degrees Celsius and it remains in a liquid state. You might actually have it at, say, 200 or 300 degrees Celsius, and it can't transfer into steam because you are adding that pressure, and because you're adding that pressure, it can't, the molecules can't expand and it can't transform into a gas. So the thing to note about that is that pressure causes a displacement of this curve right here. As you add pressure to the system, you shift everything to the right. So this fusion temperature and the saturation temperature get shifted over to the right. So in other words, it's a higher temperature where fusion takes place or where saturation takes place. The same takes place if you subtract pressure away from the system. As you subtract pressure away from the system, the entire curve gets shifted to the left. Okay? All right, I'm going to continue on reading my notes. Look at the blue one right there. In a thermomechanical system, system efficiency is linearly proportional to the total heat transfer between the hot sink and the cold sink. In an internal combustion engine, the hot sink is the temperature of combustion, the cold sink is the intake air temperature. In a refrigeration system, the hot sink is the refrigerant temperature after the evaporator, and the cold sink is the refrigerant at the thermal expansion valve, TXV. The thing to note about this particular note right there is that internal combustion engines, such as the one that you have in your car, are basically reverses of refrigeration systems. So there's a graph out there, and you can find this on Google or Yahoo. You can type in OTTO cycle. So it's the Otto cycle. It's basically a pressure versus volume. And in an internal combustion engine, you have compression, ignition, expansion, and exhaust. And if you then have a refrigeration system, you're going to find that everything works exactly in reverse on that Otto cycle. Basically, it goes backwards through the Otto cycle. So sometimes internal combustion engines are referred to as forward Otto cycle, and refrigeration systems are referred to as reverse Otto cycle. So, like I said, on an internal combustion engine, you have compression, ignition, expansion, and exhaust. In a refrigeration system, it's the reverse of that. You have compression, you have condensation, expansion, and evaporation. In an internal combustion engine, you're generating heat, you're utilizing that heat to do work. And in a refrigeration system, you're doing just the opposite. You are subtracting heat away from a system so that you can refrigerate or cool your refrigerated area. Now, one thing that's kind of interesting to note about the efficiencies of thermomechanical systems is that in a thermomechanical system, there's really only so high of a temperature that you can go. You're limited in an internal combustion engine with exactly how high of a temperature that it can operate at. You can't, for instance, your car engine, you can't use too high of a temperature because you're going to overheat things. It's going to cause pollution problems with your fuel. You've got some other issues that are associated with that. On the other hand, you put increases the thermomechanical efficiency is when you have a lower temperature. So again, the efficiency of a thermomechanical system is linearly proportional to the difference between the cold sink and the hot sink. Well, we know that we're limited as far as the temperature that we can have the hot sink, so in order to increase the efficiency of a thermomechanical system, we want the cold sink to be as cold as possible. Now, in order for any thermomechanical system to be 100% efficient, the temperature of the cold sink has to be absolute zero, which is the last node right there. It has to be minus 273 degrees Celsius, which is equal to minus 460 degrees Fahrenheit, which is equal to 0 degrees Kelvin and 0 degrees Rankine. So, again, in any thermomechanical system, we can't increase the temperature beyond a certain level. However, we can increase the efficiency of it by using as cold of a cold sink as possible. And it's going to become important because I'm going to that my design is going to take advantage of that fact. Okay, so now that we have a basic understanding of heat transfer, let's move on to a basic refrigeration cycle. Okay, right here you have a compressor, and the purpose of the compressor is to take gaseous refrigerant that's fed to it. It compresses it. When it compresses it, it increases the pressure. And because you just compressed the molecules and jammed them all together, it also increases the temperature. If you want to see that in action, take a hammer and go hit a piece of your sidewalk or go smash it into a piece of metal, and then put your hand over and you'll notice that it's significantly warmer than the area of the sidewalk or the area of the other metal around it. It's because you've jostled all those molecules, you've compressed them all together, and it increases the temperature as a result. Same thing happens with a compressor in an HVAC system. It jams all the molecules together, which causes an increase of the pressure, also causes an increase in the temperature. So now you have gaseous refrigerant, fairly high pressure, fairly high temperature. It's then going to go through a component right here called the condenser. Because it's high temperature, the idea of the condenser is to blow air across it, and this cooling air cools off the refrigerant within the condenser, and then the refrigerant, as it cools off and you subtract heat away from it, it's going to go through this latent heat of condensation that we discussed right here. So right here, it's going to go from a very, very slightly superheated gas when it goes through the compressor, and as it goes through the condenser right here, it's going to move downwards on this temperature versus heat versus temperature graph, and latent heat of vaporization is going to take place as the refrigerant cools, going to the condenser. Okay, so we're going to talk about these pressures and temperatures, P1, P2, P3, P4, as well as the temperatures here in a couple minutes. But the thing to take a note away from this is that you've cooled the refrigerant in the condenser, you've caused it to liquefy. It's still high pressure because it was compressed right here. It's not going to considerably decrease the pressure of it. However, it is going to considerably decrease the temperature of it. It's going to considerably remove heat from it through this latent heat transfer. So it's going to go from a very, very slightly superheated gas to a slightly subcooled liquid right here. Okay, after it goes through the condenser, it's then going to go through this next component, which is frequently called a TXV, thermal expansion valve. The purpose of the thermal expansion valve is to shift the entire heat transfer curve to the left, and it does it by decreasing the pressure. Remember, we talked about how decreasing the pressure shifts this curve to the left, and increasing the pressure shifts it to the right. Okay, so and we're going to talk about how this does this in just a moment. Okay, so as it goes through this thermal expansion valve, it's going to significantly decrease the pressure of the refrigerant. However, the temperature of the refrigerant is going to be roughly the same. Now, because you've caused this pressure decrease, it slightly destabilizes the liquid refrigerant, and it wants very, very badly to absorb heat and to evaporate. And so that's what this purpose of the evaporator right here is. You have an evaporator fan that blows across this. As the refrigerant goes through the evaporator, it's going to transfer from a liquid back into a gas, and then it's going to go backwards. So compressor and condenser, it's going to go this way. As you go through the evaporator, it's going to turn right around and go back upwards and go through the latent heat of vaporization until it's in a very slightly superheated state. That's what's going to happen in the evaporator. So this is actually your refrigerated area. This evaporator fan is going to blow air across this evaporator, and the evaporator coils themselves are going to be very cold because the refrigerant in there is going through its latent heat of vaporization and absorbing heat from the refrigerated space. Okay? So, after it goes through the evaporator, it's going to continue on. Now, what's interesting about this thermal expansion valve is that it's controlled by the pressure of the refrigerant after it goes through the evaporator. And the amount of pressure that's right there is directly proportional to the degree of superheating of the refrigerant. Okay. Continuing on to the cycle, it's then going to continue on. It's going to go to the compressor. All right, so let's take a look at the notes real quick that I've written on here. Okay, again, the compressor, it shifted the heat versus temperature curve to the right, caused the saturation temperature of the refrigerant to rise above ambient, and that causes the refrigerant to want to condense, but it can't because it has to lose heat. Okay, so that's what the point of the condenser is. So this refrigerant, this gaseous refrigerant, its ambient temperature is higher than its saturation temperature, causing it to want to condense. Can't do so until it goes through the condenser and loses a bunch of heat. So these are the coils on the back of your refrigerator or on an air conditioning unit on the outside of your house. They're hot to the touch. You put your hand on it, you can literally burn yourself because it's very hot to the touch. And the fan, this condenser fan, is going to blow cooling air across them in an effort to increase the amount of cooling in order to cool the refrigerant so that it can then go through its latent heat of condensation before it goes through the thermal expansion valve. Okay, so let's go discuss this. Refrigerant undergoes some sensible heat transfer, but primarily latent heat transfer. So let's go talk about that for a second. Okay, again, you're going to have a liquid that's, say, roughly right here. It's liquid refrigerant. It's not very subcooled. It's just a little bit subcooled. The primary heat transfer that's going to take place in both the condenser and in the evaporator is the latent heat transfer. And once it finishes its cycle in the evaporator, it's going to be very slightly superheated gas. Okay, so right here, the compressor, again, we wanted to shift this heat versus temperature curve to the right. The thermal expansion valve does just the opposite. It shifts the heat versus temperature curve to the left. It causes the saturation temperature, because we shifted this saturation temperature right here, we shifted it over to the left, and it causes it to fall below the ambient temperature of the refrigerant, which is going to cause the refrigerant to want to vaporize. But once again, it can't vaporize until it gains heat. How does it gain heat? It does this through the evaporator. And it sucks heat away from this refrigerated space by going through its latent heat of vaporization. Okay, so now the amount of heat transfer that takes place in the evaporator, for the most part, that's latent heat transfer as it vaporizes from a liquid to a gas, but there is a little bit of sensible heat transfer as well. So you're going to have just a little bit of the sensible heat transfer right here, as well as getting it into a superheated state. But for the most part, it's going to be this latent heat transfer, this latent heat of vaporization that takes place in the evaporator. Okay, let's see. Go ahead and discuss the rest of this. Okay, so if you take a look at what I wrote here, so you get your pressure 1, it's slightly higher than the pressure 2, just a little bit as it compresses the refrigerant right here and shoves it through the system. But once you go through the thermal expansion valve, the pressure right here is going to be significantly greater than the pressure on the other side of the thermal expansion valve, because that thermal expansion valve is going to cause a decrease in the pressure. Okay? And after it continues on, you've got pressure 4 after the evaporator and pressure 3, which is before the evaporator. It loses a considerable amount of pressure as it goes through this evaporation. Okay? Let's talk about the temperatures real quick. I think these are probably, if you're an actual engineer, it's something that you're going to want to consider, but for the layman, it's not as interesting. Temperature 1 right there is going to be higher than your temperature 2. The reason why is because the condenser cools the refrigerant. Goes through the latent heat transfer of condensation, followed by a little bit of sensible heat transfer as well. Okay. Let's see. Now, T2 is roughly equal to T3. So before and after the thermal expansion valve, the temperature is roughly the same. We want the refrigerant, when it enters the thermal expansion valve, the idea of my design is to cool the liquid refrigerant as much as possible before it enters that thermal expansion valve. And I'm going to explain why that is. Again, in a refrigeration cycle, this is the cold sink. It's the temperature of the refrigerant right here before it goes through the thermal expansion valve. So that's the cold sink, and we want that to be as cold as possible. That way it maximizes our heat transfer that takes place. Okay, more notes. Controlling the thermal expansion valve allows refrigerant to move at the proper speed. Speed isn't something that the engineers really are concerned with when it comes up to the refrigerant, but just for a layman's perspective, the speed that you go through the system, if you're an individual molecule of refrigerant, is kind of important. If you go too slowly through it, well, not enough calories of total heat transfer to cool the refrigerated space. So if you're moving too slowly through it, then it's going to absorb a lot more heat earlier on in the evaporator, but later on in the evaporator it's going to be roughly the same temperature as the inside space, and because of that you don't have nearly as much heat transfer that's going to be taking place in the later cycle, the later portion of the evaporator. Okay? Now, the converse of that is you also don't want the refrigerant to go too fast through the system, because if it goes too fast, it's going to you're going to have an inadequate total heat transfer of the refrigerant, and it's going to cause your compressor to operate more, and the more that operates, well, guess what? That's taking electricity. So the more that operates, if you have that thing running all the time, well, it's going to significantly decrease the efficiency of it, and it's going to increase the electrical bill required to operate it. Okay, basically, we're going to control the thermal expansion valve in order to adjust the degree of evaporated refrigerant superheat. So the entire purpose of what this pressure right here is it's going to control the degree of superheat that takes place, how much superheating of the gas that takes place. We want it to be a little bit past this saturation temperature, but not too far past it, otherwise it will cause a decrease in efficiency. Okay? So, let's move on to what exactly is this thermal expansion valve right here. So the thermal expansion valve, TXV, right there. Let's talk about regulator valves. It's a type of a regulator valve, so let's talk about how this works. Okay, so you have cooled liquid refrigerant because it's gone through the condenser, and it is a slightly subcooled liquid. Okay, now it's going to basically go through this line, and it's going to go through this valve, and it's going to continue on. So it's a certain pressure, certain temperature right here, and the idea is to decrease the pressure of it. Okay, well, how do we do that? Okay, so this is basically a valve. This right here can move downwards, and it can close on the seat, and that's what this is called. This is called the valve seat right here. This is called the valve disc. It's called the valve stem. Okay, and then you're going to have up here a diaphragm and an adjustable spring. Okay, now there are a few different configurations of regulating valves, and here's one of the more common ones. Okay, so as pressure, this is basically directly from the end of the evaporator, and it's going to be connected directly into the refrigerant line. It's going to go into this top portion right here. You have a diaphragm that separates it from the spring. As the pressure in this area right here increases, it's going to increase the pressure right here, which is going to drive this diaphragm downwards. Okay? As it drives it downwards, it moves this down right here, and it closes this valve. Now, because you've closed this valve, it's causing a decrease in the pressure. Okay, well, as it causes a decrease in the pressure right here, the spring force right here is enough to override this decrease in pressure right here, which causes the entire the spring will actually move the valve stem up. This entire diaphragm will move up like this, and it will open the valve. So, again, as liquid refrigerant goes through the thermal expansion valve, it's going to go past the valve seat right here. It's going to go past the disc and continue onwards. But as you have an increase of pressure, and this is on the back side of the evaporator, an increase of pressure right there is going to drive this diaphragm downwards. The amount of pressure here will override the spring force. It's going to drive it down, which is going to close the valve. Conversely, once the pressure decreases, again, it's going to, because it's decreased in the evaporator, which is somewhere past here, it's going to decrease the pressure on the top side of this, and the amount of spring force in here is going to override the pressure on the diaphragm and drive the valve back open. And I'm kind of describing that in a cyclical manner, but for the most part it's steady state. So basically, a regulating valve is a throttling valve. It's designed to restrict the amount of flow rate, the volumetric flow rate, or the pressure of the system. Okay, now finally we're going to discuss what my idea is, my specific idea. Okay, what my specific idea is, you got your compressor right here. You're going to have, and in hindsight, I should have called these phase compressors. I should have called them stage compressors, and sorry, condensers. The reason why is because the word phase is used elsewhere in refrigeration systems. So we'll just say that this is a stage 1 condenser and this is a stage 2 condenser. Okay, you have 2 condensers, and they're going to operate in series with one another. So again, it's going to go through the compressor. It's going to be high pressure. It's going to be high temperature. The idea is you want to remove the latent heat of vaporization, and then it's going to go through this second stage condenser before it continues on to the refrigerated space. But these are going to be a little bit different from one another, because that first phase condenser is going to be a counterflow heat exchanger with water. Okay, and the way that I've drawn this out right here is we're going to take water that's going to your building's hot water heater. So you're taking cold water that's coming from the city water line or your well, whatnot. It's going to go through this heat exchanger, and then after it gains heat from the hot refrigerant, it's going to go to the hot water heater. So we'll just kind of take a quick look at this. Alright, so cold potable water, it's going to go through these tubes right here, and as it does so, it's going to gain a considerable amount of heat from the hot refrigerant condensate. So this hot refrigerant condensate right here is the refrigerant that's going to go through it. Okay? So, as the hot refrigerant condensate goes through this heat exchanger right here, and it's going to hit this tube right here, which has cold potable water, which is destined for the hot water heater of a building, it's going to do this big heat exchange as it goes through it. So the refrigerant is basically going to travel down this way, it's going to discharge, and the cold potable water is going to go through the tube, and it's going to discharge out here, and then it's going to go to your hot water heater. So the advantage of this system is that you are basically going to cool the refrigerant. You're going to subtract a significant amount of heat from the refrigerant using potable water, and then because of that heat transfer, you are increasing the temperature of that potable water before it goes to the hot water heater. So there are 3 different ways that this increases the efficiency of the system. Okay, the first way is that, getting back to our heat transfer curve, right here, the idea is we want to decrease the temperature of this liquid refrigerant as much as possible. Well, this system is going to be able to do it much, much better than an ordinary condenser, which simply blows air across it. The reason why is because, well, think about it for a second. You burn your finger, what do? Is it better to just hold your finger up in the air and let the air cool it, or do you want to go run it under cold water? Well, obviously it's better to run it under cold water, because cold water has a much higher heat transfer coefficient than air does. So, if you start talking about volumetric flow rates, the volumetric flow rate of the water versus the volumetric flow rate of the air, water is about 700 times more efficient at removing heat than air is. So consequently, you're going to remove a considerable amount of heat from this refrigerant by having it exchange heat with the cold potable water. So you got the hot refrigerant, it's going to come through here, it's going to meander down here, it's going to end up as cold liquid refrigerant. It's going to go through condensation, it goes through this counterflow heat exchanger. You have cold potable water that, once again, it's going to strike the hot refrigerant, which is on the outside of this tube. And as it does so, it's going to gain heat, and gain heat until it exits as warm potable water. You then take that warm potable water, goes to your hot water heater. Okay, so like I said, there are 3 different ways that this is going to increase the efficiency. The first way that it's going to increase the efficiency is, let me find my drawing, sorry about that. The first way that it's going to increase the efficiency is that because you've decreased the temperature of the condensate to a much lower temperature than you would through a conventional air-powered condenser, it's going to result in a lower temperature of liquid refrigerant. And as we said earlier, the amount of efficiency in any thermomechanical system is linearly proportional to the difference of the temperature of the hot sink and the cold sink. So again, the cold sink is the liquid refrigerant, and the hot sink is the temperature of the refrigerant at its highest point, which is right after the compressor. Okay? So, in my particular design right here, what we're doing is we are shifting the temperature further to the left. So we're going to shift it right here. Now, as it goes through the thermal expansion valve in the evaporator, you have more heat that's going to be available for transfer, vice an ordinary refrigeration system, which is going to have less heat. So by lowering the temperature, we've added an additional amount of heat that's going to be available for transfer in the evaporator. Consequently, the compressor right here is going to have to operate less frequently. Okay? So, that's the first way that the system is more efficient. The second way in which the system is more efficient is because you're taking these 2 condensers right here, you're putting them in series with one another. You're already going to have removed almost all of the heat from the refrigerant right here through this counterflow heat exchanger with potable water. As a result, the refrigerant's going to be nice and cool before it ever even enters this second stage condenser and goes to the thermal expansion valve. Consequently, most of the time you're not even going to need this condenser fan. Vast majority of time, you're not going to need the condenser fan. So again, first way we're going to save energy is by decreasing the amount of temperature of the refrigerant by using a much more efficient heat exchanger, which is water to refrigerant versus air to refrigerant. The second manner in which we're going to save energy is that on most circumstances this condenser fan is not going to be needed on this second phase heat condenser. And the third way that it's going to save money and become energy efficient is because in the water that's coming into a building from the city or from the state or from your water well or whatnot, as it exchanges heat with this refrigerant, you're adding temperature to it. And you're doing that before it goes to the hot water heater. So you're taking cold potable water, you're heating it up free of charge with the hot refrigerant as it goes this direction. This hot, warm potable water then goes to your hot water heater. Now, because the temperature of the potable water before it ever reaches the hot water heater is higher than what it would have otherwise been, you're decreasing the amount of energy that your hot water heater is having to do to heat the water up the rest of the way to system temperature for use throughout your building. Okay, this has been a long video. I hope that this all kind of makes sense. Let's kind of discuss this right here. Okay, I kind of drew a graph down here below. Alright, so this is your cold potable water entrance. It's going to go through this heat exchanger. This might look completely different by the time you finish it. You know, it might not be necessarily a counterflow heat exchanger, might not have loops in it, might be completely different. But the concept is that we're taking cold potable water, we're exchanging it with the hot refrigerant that causes the hot refrigerant to go through its latent heat transfer to condense. As it goes through its latent heat transfer, it condenses into a liquid. Well, because water is significantly better than exchanging air for a heat exchanger, you're going to actually be able to cool that liquid refrigerant after it condenses to a much lower temperature than you would with a heat exchanger that only blows air across the condenser. So, again, you are taking cold water, you're heating it up, that hot water and then goes to your hot water heater, decreases the amount of energy that your hot water heater requires to add to it in order to increase the temperature up to its system temperature. And meanwhile, you're cooling the refrigerant in a much more efficient manner than you are by simply blowing air across it. And because you're doing that, you are decreasing the temperature of it. You're further subcooling it before it then goes through the thermal expansion valve and into the evaporator. So now, in the thermal expansion valve and into the evaporator, you're going to have, for the most part, in an ordinary system in the evaporator, you're going to have, for the most part, just a latent heat transfer. But because you've cooled the temperature to a further degree of the refrigerant, well, now you have a greater degree of subcooling. So now you're going to have a greater total quantity of heat exchange that's going to be available to it. You're going to be a fairly subcooled liquid versus a saturated liquid, and because you've subcooled it, you then have more sensible heat that can be added to the refrigerant before it then turns into its saturation temperature and goes through its latent heat cycle and transfers from a liquid to a gas. So, again, let's see if I can kind of sum that up a little bit more clearly. In this particular system right here, because you've cooled the liquid refrigerant to a much lower temperature, you're going to have a lot of sensible heat transfer that's also available within the evaporator, as well as the ordinary latent heat transfer that normally takes place in an evaporator. And because you have a greater total quantity of heat that's available for transfer, you're going to, okay, so let's even write this out. Ordinary system, you're going to have a lot of latent heat, a little bit of sensible heat. The idea of this particular design, my design, is you're going to also, the same thing, a lot of latent heat, but you're also going to have a lot of sensible heat because you've had a greater total quantity of heat transfer that's available within the evaporator. That's going to decrease the amount that the compressor has to run. Does all that make sense? Okay, let's kind of get back to these notes real quick. Okay, so again, direction of water flows this way, direction of hot refrigerant flow is this way. Goes from hot refrigerant to cold refrigerant, goes from cold potable water to hot potable water. And like I said, I've more or less explained this fairly detailed, I think. One of the things I didn't really talk about on this particular design, and this first stage of condenser, there'll be times, okay, you got potable water that you're exchanging heat with, the refrigerant. Well, there are times when you might have to do maintenance on that system, so that's what this is for. When you have to do maintenance on it, you're going to close this valve right here and you're going to open this valve right here. Refrigerant is then going to bypass this entire system right here. It's going to go to the maintenance bypass line, and it's going to go through to your second stage condenser. And because a much more considerable amount of heat transfer is now going to have to take place here because you didn't take any of it out right here, that's when this condenser fan is going to operate. And it's going to cool the refrigerant, remove heat enough to it before it then goes through the thermal expansion valve and into the evaporator. So you're going to have a maintenance bypass line. Okay, now another thing that's kind of important is, let's talk about this for a second. You have water, potable water, and you have refrigerant, and guess what? Well, refrigerant is highly toxic, and potable water is what you can drink. So something that's very important is that you have to keep these two mediums separate from one another. Okay? During normal circumstances, the water is going to stay within its tubes, and the refrigerant is just going to go through the heat exchanger and discharge. However, you know what happens if you have some pitting right here? Let's say you remove a section of this, or develops a hole, develops a leak in there. Kind of a dangerous condition because now you're adding refrigerant into your potable water line. So that's what this little system right here is for right here. It's going to measure the pressure before and after this stage 1 condenser, and when the pressure differential reaches a certain level, it's going to open this bypass valve, which is going to isolate this entire thing, and it's going to allow the liquid refrigerant to bypass it and then continue on through the stage 2 condenser. So does that kind of make sense? So this first line is just if we're going to do normal maintenance on it. This is a safety line right here to prevent these two mediums from meeting up in case that develops a hole in there, or there's a breakage or something like that. Again, we got to keep the refrigerant out of our potable water. Well, that's what this right here. It's going to immediately detect that there's a pressure differential that's not good, and it's going to open the safety bypass line. It's going to isolate this system, allow the refrigerant to continue on, and also on the other side of this is it's probably going to have another system set in place to then isolate the potable water here and have the potable water then bypass this before it continues on to the hot water heater. So, and the way that I drew this is that, alright, well, I drew this as cold potable water. Well, you know, it can also work for a swimming pool. Maybe you have a house and you have a swimming pool. What do swimming pools have? Well, they've got heating systems. They have to be heated. Well, you could easily create a closed cycle where instead of this is cold potable water, this is swimming pool water. Alright, so we have swimming pool water that goes through here. It gains considerable amount of heat, and then it kicks that warmed up water, kicks it back out into the swimming pool. So that's another possibility that you could use it for. You know, this is going to be the type of system that's going to work well on, say, restaurants. It's going to work well in large industrial buildings, hotels, places where there's a high amount of water flow. One place where it might not work quite as efficiently is in an ordinary house. But what you could also do is in an ordinary house is you could then have a large hot water tank here, and in a closed cycle, so it's going to basically go through, it's going to collect in this water tank, and then it's going to take water at its coolest point, and it's going to circulate it back through here, and it's just going to continue circulating water until it continues to get warmer and warmer and warmer each time it goes through the condenser. And then as there is demand for water, you know, your dishwasher, somebody takes a shower, that's when it's then going to draw water off there and send it to your hot water heater. So it's very possible that you can create a closed cycle system that just continues to add heat to it and add heat to it until the water temperature in here continues to get warmer and warmer and warmer, and then when there's a demand on the system, well, then it's going to discharge water to your hot water heater for usage within the house. So there are a lot of different variants and possibilities that you can, ways that you can alter and utilize this. Alright, I think this video has been long enough. I feel very winded right now. And, well, let's take a quick look at a nice, pleasant Hong Kong sunset. Right there. If you've seen any of my other videos, you know that I used to take ships in and out of port here. It's kind of my past. And what my current profession is oh geez, the airport I think is kind of over off in that area. I fly Boeing 747s in and out of here. So now I'm a Boeing 747 pilot. I used to be a ship guy. I used to have, take container ships in and out of port here. Always enjoyed coming here. At one point this was the world's tallest building right there. Just a nice little look off to the east. Very pleasant, huh? Alright, I hope you all have a good one. I'm sorry it's been so long since my last video. I'll try to keep them coming. You guys all take care.